Okay, so today we have done enough examples of the approximating the area thing using the so-called Riemann sum. And now we want to go a little bit further and say that, okay, what we have been doing specifically for positive and continuous functions, we can get it done for more general functions, specifically the functions that are not necessarily positive, and also continuity we can bring it down to a good level. So, but the work that we need to do is almost the same kind of work. The hope is that we will be developing enough properties and tools that we won't need to go through doing those summation, find the sums and do the limit. But at this point, that's the only thing we have. We have to start from there and we will move forward. And what we will now call our lecture today is Riemann sum and definite integral. Okay, for a second remember or recall that what we have been doing the last two sessions was assume that function is positive and it's continuous. So f is positive and continuous on the given interval. Then the area of the region defined by the graph of this function over the x-axis under the graph of this function, the area, is given by this. First, we find the summation, which is, okay, let me write Rn because we already had Rn of that function and that interval, and then find limit as n goes to infinity. Now, we are planning to change few things here. First thing, remember that when we were working with Rn, what was Rn? Rn was sum of delta x f of xi. In other words, we were trying to find estimate of our region by using the rectangles. Rectangles who had the base equal to the ith subinterval that we created. Maybe I should do it a bit smaller so that I can do more thing. But the height, we decided to evaluate function on the right end point of that subinterval. So the height of that rectangle, we decided to go by that. F of xi. That Rn, R comes from the right end point sum. So this we call it right end point Riemann sum. The question now is, why the right end point? Why didn't we choose the left end point, for example? Why don't we do xi minus 1 xi? And if the function is like that, why don't we use this value Well, I don't know. Well, let's do that one as well. Yes, we can do delta x, f of xi minus 1. I goes from 1 to n. And, well, we will denote this by Ln. And guess what L stands for? Huh? If R is the right endpoint, left would be, L would be left endpoint, yes? So we can, someone can come say that, oh, what if I want to use left endpoint? Yes, you can do that. Obviously, this summation could easily be different than that summation. But estimate itself is not that important. What matters is at the end, are the limits the same thing? Because we found the limit of Rn, and then the limit was the area. One can come and say even more. Why are we picking the right endpoint or left endpoint? Why don't we randomly choose a point xi star in the ith interval, say somewhere here. In ith interval, I choose just some point, I call it xi star, and it could be in different position for different sub-intervals. And then my function is, which is like that. Now I use that value. So here, f of xi star. Some value picked up from that interval rather than using the right endpoint or left endpoint. Well, we have no problem with that. One can do that one. I goes from 1 to n. The process is the same, but the estimation that we are getting for different things will be different. Different points that we pick will be different value. Now, the question is that, are they going to be the same? Well, sorry. The answer for that obviously is no. They're not going to be the same. Is their limit all the same or not? Well, if your function is continuous, you can show that. Doesn't matter if you use the right endpoint, left endpoint, or the last one that I have there. They will give you all the same thing. They are different things, but when you find a limit, you will get the same limit. And this is a mathematical fact. This is not straightforward. There is no reason that you pick the left one, right one. And indeed, there are cases that if your function is not continuous, then you can create cases that the left is not equal to the right. And it could be a big problem there. Yeah. This all happens for continuous positive, and in all those cases, we get the area of the region under the graph of that function. Why positive? Who cares what is the meaning of this thing? I can create this for more general function, yes? Give me any function you want. The only thing I care is that it must be defined on that interval. Okay, so that is where my new idea is coming in. And this is definition. I am not anymore assuming f is continuous, nor it is positive. Take any function, let f be a function defined on the closed interval AB. Okay? If I drop the continuity, there is no guarantee that when I pick the left endpoint, I'll get the same value as the right hand point. So there's nothing that guarantees that. So I will take that and put as my definition. If the limit sum of delta x f of xi star, as I goes from 1 to n goes to infinity. If this limit exists, wait, for which xi's? I want all such limits exist for any choice of xi, and all of them are equal, and gives and have equal value for all choices of xi star. In other words, instead of saying that, okay, split this interval to n pieces and use the right-hand point, you say that split this interval to n equal subintervals and give 1 point from each one of these ones. Then I'll go compute this product, add them, find the formula. Well, if you're lucky enough, you can do that. Well, you already see how difficult it is. Then find the limit. If for all such choices this exists and all of those limits give you the same value, let's call it L, for all and has equal value L, then we say f is integrable on the interval AB. So I don't care about the choices. I can do the sum. I get value. And we denote the value of the limit by, we denote it by a fancy notation. I don't want to write each time limit of sigma of delta x f of xi star. I want to use a clear, nice integral fx dx from a to b. This is called definite is called definite integral of f on a b. Wait a minute, we use something very similar to this. Without those limits, those two numbers over there, which we call that integral limit, upper, lower integral limit. This one, upper integral limit. If I take those two numbers away, I already used that notation. What was that notation without a, b in those points? What did we call that one? Indefinite integral. Why they are very similar, we will see it later on. This is history erased and rewritten so that they are closely related in their notation. But there is a deep fact that relates this definite integral to that indefinite integral that we learn about it later on. One thing is definite integral is a number. Unlike indefinite integral was the whole possible antiderivatives of the integrand, yes? Here, this is only one number. 2, it is equal to the area under the graph of f on interval AB. But remember, area, we only defined it when the function was positive. So when f is positive and continuous. Done. We have the new notation, definite integral from a to b of f of x dx. And we know that when the function is positive and continuous, that's what we have been doing. Yes? But what if the function is not positive or not continuous? Well, then I have to go check all the possible sums that I can create that way based on different choices of xi's. Find the limit. They have to all give me the same value, something which is not possible in any human lifespan. Well, that's where mathematicians come in. Hello, I can show things and save your life. That's the first thing that says, well, when mathematicians have an important thing to say, they have this habit of theorem. Let's write that down. I have a theorem for you. So you have to listen carefully when they say they have theorem. I don't know why mathematicians are like that. They say you actually don't need to check all the possible things that happens here. If you know that every continuous, any function, every function f that is continuous on AB except in finite many points, every function that is defined on AB, and you know it is continuous, not everywhere, but everywhere except 10 points, except million points, except a finite number of points. If we have discontinuities in finitely many points, then every such function is integrable. Every function f that is continuous on AB, but except on finitely many points, well, it must be defined everywhere on that interval, but it could be jump discontinuity.
Oh, okay.
Or removable discontinuity, yes? So every function that has only finite of such discontinuities are integrable. Wait, what is how important is this fact? The importance is that Once you know your function is continuous on AB, but except in finitely many points, then you don't need to go check all those different things. So as a result, if f is only discontinuous on finitely many points of AB, if it is discontinuous on only finitely many points of AB, then the integral, guess what? I don't even need to check left-hand point Riemann sum. I only need to check one, and I'll just write the right endpoint. It's a lot of relief. I can check discontinuities fast, yes? If I see that there's only finitely many discontinuities, I am not going to go crazy choosing different points. Just go very clean, choose the right hand points, find the Rn, find the limit. That will give you the definite integral of the function from A to B. Does that make sense? Aren't mathematicians crazy? Aren't they? Say it loud, let me hear. I want to identify who says yes. No one said yes. Yes, please.
Except infinite many points.
No, except in finite. Maybe I should write. In a finite number of points. Not in, yeah, there was just one in there, not two. Yes? Well, the difference here is that I give you the I subinterval, okay? How many points you can choose between xi minus 1 and xi? Infinitely many choices you have. For each subinterval, you have infinitely many choices. So you can form infinitely many sums like that. And you have to check every one of those ones and make sure that everyone has the same limit. This says, no, if you know that the function is discontinuous only on a finitely many points, you don't need to go crazy. You just pick the right endpoint, it will give you the right thing. Sorry?
What happens to the points you know that are...
That's exactly, don't care about it. You don't care about it. You just choose the right endpoint approximation, it will give you the right number. Make sense? Any other questions? Get it out of your system. I know that it could be confusing. Yes? Louder.
We can have her jump in.
No, see here, I want the function to be defined on the interval AB. Any discontinuities that you can have, I'm okay with it. Any discontinuities that you can have, but assuming that it is defined on every point on AB. Don't look at the categorizing discontinuities. That's what I'm trying to say. Don't look at any kind of discontinuities. Only finitely many of them is accepted. Okay? If it is defined everywhere. Yes, please.
Every argument is the left, right?
What louder? Question is not just for me. That's for a whole class. Someone else maybe answers that.
What if like every other point on the whole thing was finite? Like wouldn't that have a big impact on the final answer?
What is every other point? You tell me that, I'll answer your question.
Continuity.
Are there finitely many of them?
Yeah.
Then yeah, I'm okay with it. That's not what theorem, that's how crazy that theorem is. You choose any function, but the condition that's defined everywhere, but only has finitely many discontinuities, try your best. At the end, all such sums will give you the same limit. All such sums will give you the same limit. Yeah? Are we all good now? What? Yes, please. I maybe now can hear you, yes.
Integration whenever we're looking for area, or we have to use.
We can't, sorry, again. Yes, please.
Can we use integration whenever we're looking for area, or will there like be times where we have to?
Just be patient. That's something that I will cover in 2-3 minutes, okay? But I want to use that fact, at least cover the examples that we have done before. The examples, remember, function x squared dx go from 0 to 1. This is the example we did on Monday, yes? This is continuous function on that interval, so I don't need to go to find different points. It's enough to just find limit of Rn as n goes to infinity for what function? For x squared on the interval ab. What was this limit that we found on Monday? Can anyone check that? Go back, check your notes. Tell me what was this value? What was this value for x squared on the interval 0, 1? Everyone, stop talking to the friends. Go back to your notes. Give me the number that we found for that on Monday class. Go ahead, please. 5 seconds, go.
For the answer?
Pardon?
Like the area?
Yes, that's 1/3, yes? While you're there, we did something yesterday. I think it was this one. We did find Rn as n goes to infinity of 2 to the power 2x plus 3 on 0, 1. What did we find for this one? What did we find for this one yesterday? I remember what we found, but I just want to see if you guys can. You're taking my picture instead of checking your notes. Okay, what was the number? 24 over 2 ln 2. We also did 0 to 6 of 9 minus x minus 3 squared dx. Well, we didn't do the Riemann sum. We used the trick that we can evaluate that value, and we found 9 pi over 2. We also did another one, 0 to 2 of, what was it, 3x plus 1, if I'm not wrong. And then we did find this one, 8. That trapezoid, the last example that we did yesterday. So we already used very complicated term game, and then we evaluated these ones. Now, from this point on, we want to do more. But all these things come from the fact that we have to study more and more properties of definite integrals. So I'll start the properties of definite integrals with the first thing related to definite integral and area. Well, we already checked, we already see that if your function is continuous, then, and positive, if f is positive and continuous, then the area, I am hearing so much chatting today. What is going on? And I'm hearing very specifically from that part. Thank you. So area in that case is given by AB f of x dx. Believe it or not, when I'm back to you writing, I can still hear. Okay, what happens if the function is not positive? Well, if the function is continuous but not positive, you may get parts that are under x-axis, parts that are above x-axis. For example, I may get, well, 3 regions, R1, R2, R3, yes? What then integral of f of x dx mean in that case? Okay, in that case, what I can say is that the positive sides will still contribute as area. In other words, this will be area of R1 plus area of R3. But what will happen to the part that is under x-axis? Well, in other words, if I, for a second, let me slide this one. When I'm looking at, oh, did I erase all the Riemann sums I had? When you look at the Riemann sum, if your function is negative, you evaluate it at any point, it will give you negative value. Yes? So this guy will be, the integral of this part will be negative. Something that we don't have in the area. But you can easily show that it's enough to find the area of that under x-axis and subtract it from the other parts. What I like sometimes to say is integral or definite integral is signed, bless you, area. Area that comes with sign. It could be positive, it could be negative. But how exactly it is signed is this way. If you have regions which are above x-axis, you add the areas of those parts. If you have areas that are under the x-axis, you subtract those. Does that make sense? Yes, let's do some examples. Evaluate. Using area property. Let me see. Oh, where is it? Sorry. Okay. Integral of -1 to 3 of 2x plus 1 dx. I have 2 more examples, but let me just sorry, that's, I have different 2x, wait, why did I leave it here? 2x minus 3, not that's very, from 1 to 4. Let's do this one. And then I have 2 more examples. I'll do this one first, and then we go from there, okay? I changed the function and the limits. Okay. What I mean using the area property? What I mean is that find the regions defined by the graph of that function and try to evaluate the areas and then use that formula and give me the value of your integral. So here, when x is 0, that gives me -3. When 2x minus 3 is 0, you get this one. So this is 1, this is 2, 3, 4. So from 1 to 4, I have two regions. This piece here and this piece up there. Yeah? The piece down there, both of them are triangle. Both of them are triangle, but this piece is under the x-axis. This piece is above x-axis. So I'll do area of this big piece above x-axis minus area. Why minus? Because this small piece here is under x-axis. In the definite integral, if your region is under the x-axis, the value of that integral will be negative of the area of that part. Now, what are these guys? Here, I have 4. This is 3 over 2, or 1.5. Yes? So this part is 5 over 2, or 2.5. How about the height? You evaluate 2x minus 3 at 4, and you get 8 minus 3, 5. So this is 5. This is right triangle with those information. Here, I have 1.5, so this is half. How about this one? F at 1. If I plug in f at 1, it gives me -1, but the length of that part is going to be 1. I have two triangles, and I can find their areas. This one will be half of 5 times 5 over 2. This other one will be half of 1 times 1 over 2. That is 25 over 4 minus 1 over 4. That will give me 24 over 4, which is 6. The integral of that function is equal to 6. Any questions, any comments? Look, this is an improvement. Rather than me going through all the Riemann sums and all those things, I can look at the areas and evaluate. But areas are not always easy to evaluate. It's a small improvement point. It helps us a little bit. It's not helping us much. But still, it's a good tool. And the next question, I'll give you 2 minutes to do that. From 0, where it goes all the way to where? Zero to 3, where f of x is this piecewise defined function. Nice one. 1 minus x squared for x is less than 1, -1, bigger than -1. And for x is bigger than 1, it is given by -2x plus 2. Okay? I'll give you 30 seconds first to sketch the graph of this function on that interval 0 to 3. And then I'll give you another 90 seconds, and this will be our iClicker question. Those who are leaving, you know that we are releasing an iClicker question in a minute. Okay? Go ahead, sketch the graph of this function on that given interval. This part, what is the graph of the function on that interval? Y is equal to root 1 minus x squared. Yes, please.
Quarter circle with radius 1.
It is a circle centered at 0 because you can turn this one as x squared plus y squared equal to 1. It's centered at origin. The radius is 1, but since we are getting only the positive side of that, it will be only upper semicircle. But we are only interested in from 0. So let me draw this. That's the graph of the function on that interval. But just know that we are interested in from 0 upward. After 1, this is at 1, this is 0. And then up to 2, 3. At 3 is -4, so it will go something like that. Okay? That is the graph. Now you will have 90 seconds to evaluate that limit by looking at the graph of that function. Go ahead, and you have to answer the iClicker question, please. It's already running. Can anyone please confirm that you're seeing the question? It's my picture there. Everywhere. Forty seconds left. Okay, put in your answers, please. You write just PI. Doesn't matter, come on, just write something. Okay, here, I know that there are two regions, one above x-axis, one below x-axis. So we find the area of this one, which is positive, and then we subtract area of the other one, which is negative. Now we have to find out what are the dimensions here, yes? So this one has radius 1. That means that I am working with the area of circle, but I'm only interested in a quarter of that. Yeah? This part, I have, this is 1, 2, 3. That shouldn't go all the way to 4. This part from 1 to 3, this is 2. How about the height? When we plug in 3, we get -4. So the length is 4 here. So that part was pi over 4 minus. This part is half of 2 times 4. So this gives me pi over 4 minus 4. Any questions, any comments? Put your answer in. I'm closing the die clicker question.
Yeah. We just like the area of the circle and pi r squared.
It doesn't matter.
Where is it? Sorry.
Okay. How about this one? Quick, I'll give you only 30 seconds here. We have 90 seconds left. 30 seconds. Can you evaluate limit of sine x from -pi/2 to pi/2 using the areas? Yes.
For the area, why is it negative? Or should be plus? I don't know. To make the height negative.
No, it is 4. So see, the value here is -4, but the length is what matters for me, yes? So the length is 4. This is 2, 4. 2 times 4 is 8, divided by 2 is 4. But this is under x-axis, so I have to subtract that. Okay. This is exactly what is written here. The positive regions will add to the integral value by their area. Then the ones that are under the x-axis, they will subtract, yes? Okay. What is integral of -pi/2 to pi/2 of sine x dx? 0. Can you tell me how you find that? Yeah?
Is the left side of the sine and the right side of the sine same?
So, looking at the graph, there are 2 regions, and we have to do the area of region 1, region 2, and we subtract from that area of region 2. I don't know what is the area of region 1. If you have stayed this long in the class, I think 1 more minute you can also stay. Thank you. So the limit, I don't know what is area of R1, what is area of R2, but what I know is that this region is exactly this region. One is on the positive side, one is in the negative side. So they will have the same value. That is going to be 0. This will repeat itself whenever your function has a symmetric. Oh, now this is very difficult to do that. Again, I don't know, something like that. When your function, the graph has symmetries with respect to the origin, do you know what is called such function? Odd function. So this is another property. It says if f is odd function on the interval -a to a, then what happened for the sine will happen for that one. From -x to x dx. Oh, sorry. The same thing will happen for tan. From pi/3 to -pi/3. That will, you'll get 0. Have a great day. You come back tomorrow. We will learn more properties and hopefully start learning our fundamental theorem of calculus.
Bye-bye.
Yep.